Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. In today's episode, we will continue talking about reinforcement learning. This is our fifth part in our series on reinforcement learning. In the previous episodes on reinforcement learning, we talked about Monte Carlo simulation. We have talked about Markov decision processes and how to evaluate those Markov decision processes and how to learn in those Markov decision processes using Bellman equations. And there are certain paradigms. For example, we have used Markov chains to learn. We have used dynamic programming to learn. Now, these have their own strengths and weaknesses, so that even though the core idea is to have the machine or the agent learn from its environment, there are different conditions which allows the agent to learn, and it leverages different techniques to learn. For example, if the agent knows that the environment is fully known, like the entire house for RoboVacuum, if the entire house is mapped, then it knows where its rewards lie, where the charging station is. So the environment is known. It has already mapped the environment. Then it uses dynamic programming to learn and further improve its policies on how to clean the house most effectively. On the other hand, if the environment is totally unknown, then the only way to improve and learn an unknown environment is to use a Monte Carlo method. And in most of the stock portfolio simulation, the back testing, they use Monte Carlo because the market conditions are constantly changing. So depending on the environment, whether it's fully known or partially known or not known at all, we use different methods, Monte Carlo or dynamic programming. Now, there is an even better method which leverages the strengths of both of these methods of Monte Carlo, the exploratory strength of Monte Carlo, which doesn't need much information of the environment, plus the dynamic programming's method of quickly calculating and iteratively calculating the value of the next state and quickly gaining knowledge without doing too much in-depth calculation. Those things can be combined into one solid learning method called temporal difference learning. In fact, Professor Sutton said that this is one of the cutting edge in reinforcement learning. So that's what we're going to talk about today, the temporal difference learning. And we're going to learn it through a very specific example of an online shopping bot. We'll start with a very simple online shopping bot, which uses Monte Carlo methods, a random policy of random Monte Carlo method of suggesting random shopping articles to the shopper, and then it will slowly improve its policy, and we'll see as it improves its policy at each stage how the outcome is improved substantially. And finally, when we go to the temporal difference learning, we'll see that really it improves its outcome much way better than what it had from the random suggestion that it started with. So let's get started. So we'll start with a quick tour of Monte Carlo, and then we'll move on to Monte Carlo control. So the main difference is in Monte Carlo control, the agent has some control over the environment. So it essentially changes its policy iteratively as it learns. And then we'll show that how a deterministic policy, which is like predefined, will allow the shopping bot to make suggestions that deterministic based on what it perceives the user or the shopper wants. But then we'll keep improving the policies, and finally when we go to the temporal difference learning, then we'll see a substantial improvement in the online shopping bot suggestion. In fact, most of the online stores, like big stores like Amazon, use a variation of this, and we'll discuss all those things. Imagine you're at a new restaurant and the menu is huge, like pages and pages of options. You have never eaten here before and you're not sure what's good. So what do? You might pick something randomly, like a pasta dish. The next time you come, maybe you will try a burger. Over time, you get a feel for what's good and which dish you like the best. So that is how Monte Carlo works. That's Monte Carlo in a nutshell. It's all about trying things out, trying new things, gathering the experience and learning from the outcomes, and eventually forming an opinion, a preference from the past experiences. So in the world of reinforcement learning, Monte Carlo works just like this. So the system tries different actions, like picking from the menu, then it observes the results, and over time it learns which actions leads to the best outcomes. It doesn't need a plan or prior knowledge. It just learns by trial and error, by trying and observing. For example, another example, think about a robot trying to navigate through a room like a robo vacuum. It bumps into the walls, finds open paths, and over time it figures out the best route to take. The robo vacuum didn't know anything about the room at all in the beginning, but just by moving around and learning from its mistake, like bumping into things, it learns, okay? Provided it doesn't bump into movable objects like cats and pets. So that's how Monte Carlo essentially works. It explores, it learns, and it slowly improves. Now let's see if we can apply it to an online shopping bot. So we need to note that Monte Carlo methods only learn from complete experiences. For example, we need to finish our pasta or burger, and we need to do that, have that experience in full before we know that it's a good choice. Okay, only after we finish our meal can we make the decision. We cannot just leave, get a phone call and leave and make a decision, right? So in the same way, the Monte Carlo needs to finish that experience. We need to complete the entire episode. Then only it can make that decision. The system technically waits until an entire episode is done before it learns and updates its strategy based on what worked and what didn't. Now, in the context of an online shopping bot, it's like the bot is randomly suggesting different items to the shopper. Maybe one day it offers us a blender, and another day it offers me some shoes, and the next day a gardening book. Over time it learns which suggestions are getting more clicks and starts to refine its recommendations. So this is essentially a recommender system. But it only makes these adjustments after enough data is gathered over several trials. So whoever designs the system has to set a time frame for which the experiment runs, maybe a month, maybe 2 months. Only then the agent is going to update its policy and say, okay, these are working and these are not working. Okay, before the campaign ends, it's not going to make any decision. So Monte Carlo is great for learning through experience, especially when we don't know much about the environment in advance. But the drawback is it takes time. It needs complete episodes to see the full results before making any decisions. In terms of stock market, if we are doing back testing, we need to let the whole simulation run for the entire period for which we're doing the back testing. So the Monte Carlo, it can work on an unknown environment, but the drawback is it needs to run for the entire period of the environment before it can make any kind of helpful suggestions. Now let's talk about the Monte Carlo control. There is a slight difference between Monte Carlo and Monte Carlo control. In simple Monte Carlo, the system learns from entire episodes. Only after the whole experience is complete does it look back and decide what worked. It's like going to a restaurant and only deciding if your meal was good after you have finished your entire meal. There is no immediate feedback during the process. It's all about reflecting once the episode is over. Now in MC control, this is taken a little bit further. Instead of just learning from past experiences, the agent is actively trying to improve its policy. MC control doesn't just reflect, it adjusts its actions and strategy to get better results next time. This is called policy iteration, and we touched on this in the previous episode. In policy iteration, the system refines its approach based on what it learns from each episode. Now let's bring back our online shopping bot analogy. At first, the bot has no idea what the shopper likes. So it suggests a random assortment of products. One day it shows you a blender, the next day a pair of shoes, and then maybe a tech gadget. It's like throwing things at the wall to see what sticks. The bot isn't making these recommendations based on any knowledge of the shopper's preferences. It is just trying random things out to gather data, see what the shopper likes. This process is called random explorations. And now the system has no strategy yet, just experimenting to see what works. Now the key to the Monte Carlo control is that the bot will eventually learn from these random trials over time as it collects more data, like which items you click or which products you buy. The bot starts refining its strategy. This process is what we talked about before. This is called policy iteration. Now, with the random exploration policy, this is evolved based on the feedback that the shopping bot gets from the shopper, what the shopper clicks, and eventually the bot becomes more targeted in its recommendations. For example, the shopper, with maybe me or you, can consistently click on the tech gadgets, which I do sometimes, and the bot will start showing us more of those tech gadgets, showing less blenders or shoes. It's gradually optimizing its choices based on what it learns from our actions. So while it started off randomly guessing, it will slowly get better at predicting what we like and what we actually want, all thanks to the trial and error process. But here's the catch. The Monte Carlo control with a random policy is not the most efficient way to learn. The bot is improving, but very slowly, because it relies on those random choices at first, and it's like wandering through a maze without a map. We are bumping into walls and only figuring out what the best route is after completing the whole maze. And this means the initial phase of learning is very slow, and that's where we can improve, and that's where the next policy improvement comes in. So how do you improve on this random policy? Once the bot gathers enough information from our clicks, it starts to learn that we prefer tech gadgets, for example. Now, instead of guessing randomly, the bot will always recommend tech gadgets. That's one of the deterministic policy strategies it can follow. It's no longer experimenting. Once it has figured out that we like tech gadgets more than anything else from the random recommendations, and we selecting only tech gadgets, it has figured out that's the best thing to do. So it selects that policy and deterministically follows that policy. So it becomes a deterministic policy. It no longer randomly samples. So it is no longer experimenting. It's following a fixed strategy based on what it has already learned about our preferences. This is policy evaluation in action. The bot has evaluated our choices and decided on a strategy. Now, there is a downside to this. The bot is now stuck in a loop since it always recommends tech gadgets. It's no longer exploring the other categories like books or kitchen utensils. Sure, it's giving us something that we are likely want with a high likelihood, but it's missing out the opportunity to find out if we might like something else even more. This is where policy iterations comes into play. It's not enough to stick with one strategy. The bot needs to refine its approach by mixing in new options, and that's where we go to the next strategy of reinforcement learning. Now we'll look at a much better policy than the deterministic policy or the random policy. This is the epsilon greedy policy. We looked at epsilon greedy policy in one of the previous episodes in this series, but we're not going to formally declare it as part of the Monte Carlo method. So now in epsilon greedy policy, most of the time the bot sticks with recommending tech gadgets to us because that's what we like, and that's what it sees that works. It's using the data to make an informed choice, which we call exploitation. But every now and then, the bot will throw in something unexpected, maybe a kitchen gadget or a fitness tracker. This is exploration. The bot is willing to take a small risk by showing us something different, just to see if it catches our interest. Now imagine out of nowhere that the kitchen gadget becomes a hit. it turns out that lots of customers love it. But if the bot have not had taken that risk by exploring new products and showing the kitchen gadget, it would have never found that kitchen gadget that became an overnight hit, a runaway hit. It would have never become a top seller. This is the power of the epsilon greedy policy, a balance between sticking with what works and occasionally exploring new possibilities. We can in fact even apply to our life that we should follow a path that works for us and occasionally we should randomly sample. Okay. So if we keep going to a few choice restaurants that we like, but occasionally we should go to other restaurants just to try out new things. We might like a new restaurant, right? So the epsilon part refers to the small percentage of time when the bot refers to take a chance and throws in a wildcard. So go back to a few episodes back where we discussed the epsilon greedy policy, but we didn't discuss it in a context of solving policy iteration in Monte Carlo method. Okay, so let's get back to the epsilon greedy policy. So when the bot implements the epsilon greedy policy, it just keeps getting smarter. It learns from what we have clicked and keeps improving the recommendation. But because it's always exploring just a little bit, it avoids getting stuck like it does when it follows the deterministic policy. It always discovers new products that we might like. Now here's a challenge that many sellers on platforms like Amazon are facing. They're constantly at the mercy of these algorithms, and no matter how much they try to game the system, it can still feel like their product recommendations are random. You hear about these sellers spending thousands of dollars on Amazon sales optimization courses, books, trying to crack the code. But the reality of the situation is that much of what gets shown to the customers is driven by random exploration. Well, just like we talked about in the epsilon greedy policy, the algorithm is always balanced known product recommendation with some random artifacts thrown in. So instead of getting caught up in these expensive Amazon optimizer courses, we can talk about a more sustainable approach, focusing on marketing and branding. Now why? Because when we invest in building a strong brand, we are not just relying on the whims of an algorithm. We are creating something recognizable, something people trust, and that drives long-term customer loyalty, whether or not the algorithm shows them our product. Let's consider organic growth for a second. Yes, I get it. It's slower and it doesn't give you the instant success that you'd like, but it builds a much stronger foundation when the customers knows your brand, trusts your brand, and they'll actively seek out your products. You don't have to spend thousands of dollars on the courses. You don't have to depend on Amazon algorithms, whether it decides to put your product in front of them. The organic growth is the holy grail of increasing brand value, but substantially. Now, don't get me wrong, there are still basic patterns in the Amazon algorithm that you still need to pay attention to, and these are worth optimizing. For instance, keywords. You need to make sure your product listings, of course, have to have the right keywords, otherwise the recommender bot is not going to pick up on it. So that's going to increase your chances. If you include most keywords, it will increase your chances to show up in the search results. To load it with keywords, make it SEO optimized. And the other important thing is the customer reviews. These are huge. In fact, the Amazon algorithm really is biased towards customer reviews. So social proofing is something that these algorithms simply cannot ignore. And of course, competitive pricing, that's also the algorithm favors. If the product is competitively priced and then in line with the competitors, then you are definitely like to win the buy box. And don't forget fast shipping, Prime eligibility, and all those things are also factored in. So I'm not an expert in Amazon FBA or drop shipping or optimizing Amazon. You can look up a few books. What I'm saying is that the Amazon recommender algorithm cannot be probably gamed. It's better to focus on macro economic structure like branding, marketing, building a loyal customer base, having great quality products, good customer feedback, and of course competitive pricing. Let's start with an example we can all relate to. Christmas. shopping. Imagine a mother who knows exactly what each family member needs or wants for Christmas. Her son's been hinting at a video game, her daughter has her eyes on a new book series, and her husband could really use a new tool set. But here's the catch. She's working with a tight budget, and there is no room for mistakes. So instead of running around the mall, hoping for the best, she planned it all out. She knows where the sales are, where she can get her coupons, and how to get the most out of her money in her limited budget. Now, with all this info in hand, she doesn't need to experiment or guess. She's already calculated the best way to buy the gifts without breaking the bank. Now, that's how dynamic programming works. We don't need to guess or learn from trial and error like Monte Carlo does. We just need to calculate the best outcome because we already know all the information. We all know all the information about the environment. Now, let us shift gears and talk about the tech world. Think about a company running a data center, managing huge amounts of web traffic. They know when traffic spikes happen, say during the morning rush or in the evening, and they know exactly how much computing power is needed to handle it. So instead of reacting to server overloads, they scale up elastic compute nodes ahead of time. Compute nodes are essentially virtual servers that the cloud platform like AWS or Google Cloud Platform can deploy extremely fast within like milliseconds. So essentially we don't have to create actual servers. They are virtual servers that are generated on the spot almost instantaneously. So they scale up quickly using these elastic compute nodes. So elastic means flexible. So these computing resources can stretch to handle more users when we need them and then scale back down when things quiet down. So we are not wasting resources when they are not needed. And think of a node as a house in a neighborhood. Each house is independent, but is connected to all other houses through roads, utilities, and communication systems, like telephone communication system. In a computer network, each node is like one of these houses. It's an individual computer or server that's part of a larger network, just like how a neighborhood functions best when all houses are connected by roads and infrastructure. A computing system works best when all nodes are connected and are working together. So the elastic nodes are generated in an elastic fashion. So maybe one node is running one server, one node corresponds to one server. Let's say one virtual service is running, is handling the all traffic. And then suddenly the demand goes up. Maybe there is some sudden news or maybe some breaking news that everyone is searching the internet, or maybe everyone came home and started watching TV. So suddenly the demand went up on the server. So now immediately anticipating the demand, the server can spawn multiple nodes or multiple virtual servers which can handle those demands. So essentially maybe there was like 1,000 queries that were coming to the server. Now there are like 10,000 queries. So now they will create 9 more compute node servers, so which can handle those 10 times more volume that's incoming into those servers. So that's how they work. And that's how dynamic programming is used in real life. And there are many more other examples of dynamic programming, but we're not going to dwell on it and move on to temporal difference. Imagine you're cooking a new dish, and instead of waiting till the meal is completely finished and to see how it turned out, it's a better idea to taste it at different stages, at various stages, and adjust as we go. In fact, if you watch one of those cooking shows hosted by Gordon Ramsay, he keeps saying, taste everything, taste as you go. So maybe halfway through, you realize it needs more salt, so you add some more salt. Later, you taste it again and decide to tweak the spices. And by the time the dish is done, you're improving step by step based on what you realize along the way, and the dish becomes perfect. In fact, that's exactly how temporal difference learning works. Instead of waiting for the whole process to finish and then learning from the result, the TD learning adjusts in real time constantly improving based on new information that is available at every stage. And now think about the online shopping experience, what we talked about before. Like when you're browsing on Shein, I don't know if you use Shein, but if you use one of those Chinese online marketplaces apps, they are very fun to play with, and also they are very cheap and the delivery is ridiculous. So every time, I'm assuming that you're familiar with one of those, but let's say if you're not, so essentially you go on the app, just like Amazon Shopping, you choose different items, put them in your cart, move them out. It's a very seamless experience. So the difference with Amazon Shopping and Shein is that every time you click on an item, say a pair of shoes or a jacket, the platform immediately adjusts its recommendations, and then it shows you more items that match your style. You don't need to complete your shopping. You don't need to check out like you really need to do with Amazon and other online shops before the algorithm starts learning your preferences. It constantly adapts as you go, offering more and more relevant suggestions with every click. In fact, this is exactly how the TD learning works. Constantly learning from each new piece of data that comes in. Now, does Shein implement TD learning? Probably, but we're not sure. They might use some variant of TD learning. What makes the TD learning so powerful is that it combines the best aspects of Monte Carlo learning and the dynamic programming. The strength of MC, Monte Carlo, is that we can explore a completely unknown environment and do really well just by learning by trial and error. And the strength of the dynamic programming is that we can immediately start learning very fast based on very recent experiences. Like if we bump against a wall and it's like, okay, we're not going to go right. There's a wall right there. Okay. It's in the dark. So we learn very fast iteratively. And this method combines both of the strength of both of these methods, fast learning and also iteratively learning in an unknown environment. This makes TD learning incredibly useful in unpredictable or unknown environments where you can't wait for the whole process to finish before learning and adjusting. That's why it's often considered the next generation of reinforcement learning. It allows systems to learn efficiently in real time, even with partial information, whether it's adjusting a recipe step by step or refining the product recommendation in real time. TD learning is the way to go. You're always improving based on the most recent data. You're not waiting for the final result to make changes. You're not waiting for the entire environment to be known to you. You make changes on the fly. It's like highly adaptable systems. In fact, the agile method that businesses employ is a variation of this TD learning. The teams become very agile. They constantly learn from their mistake and totally change that direction very fast. So that's a variation. It's not exactly TD learning because TD learning is more sophisticated and there are multiple steps, but it's a variation. It's like a more macro version of TD learning, which is much more fine. Now let's talk about a few real-world use cases of the methods we discussed so far. Let's start with online advertisement. And this is huge scope for using reinforcement learning. And of the methods that we described today, Monte Carlo with online control and dynamic programming, the best suited one to use with online advertisement would be the TD learning, because it can help advertisers tweak their campaigns on the fly based on immediate feedback. If an ad is not performing well, TD can quickly change gears and totally change directions, right? Monte Carlo can work. It is better suited to look at the big picture, evaluate the success of the entire campaign after it has run its course. Let's say you run the campaign for a whole month and then evaluate. Maybe you ran 3 campaigns and then evaluate progress. And in fact, that's what some people say. A/B test your campaigns, run multiple versions of the campaign with different words, different content, and see which one performs well. Let the campaign run and get the exposure, the organic growth that it takes. Maybe run the campaign for a month and then evaluate the results. But with TD learning, we can be a little bit more flexible. We can adjust the content as we progress. If we see the campaign is not engaging well, we immediately tweak the content and then we show that content to a different demographics and see if it performs better. Or we switch gears and completely change the entire content and show it back to the same demographics and see it performs better. Or we can tweak the time of the day where it's presented to the specific demographics that we are trying to reach. So all those things, these are very involved marketing strategies, and we are not going to get into that. But that's the idea. If we want to use dynamic programming in this context, we need a highly detailed model of user behavior, which only big marketing companies have. And it's very hard to get on that kind of data. So it's newer marketing companies should just stay away from implementing dynamic programming in this sense. TD learning will work really well in this context. Now, stock trading is another avenue where reinforcement learning is used constantly. And here the temporal difference learning is again the best to use. As the stock prices fluctuate, the TD helps the traders adjust their strategies in real time. In fact, it will not be traders, it's just algorithmic traders that are the bots that are making decisions. They can adjust their strategies in real time depending on market volatility, the market volume, VWAP, and all the other different metrics that traders like to follow. And that ensures they can capitalize on the microstructure shifts in the market as they really happen. In fact, this is more ideal for high frequency trading. Retail traders should stay away from these trading strategies because they are not unless they are implementing swing trading strategies spanning multiple weeks and essentially looking at changes in market macrostructure. Following changes in microstructure is very, very high frequency effect. That is not suggested for retail traders. In fact, I'm not an expert. Better look into your trading books and talk to an expert financial advisors even before considering employing any of these. Monte Carlo is more for backtesting and more useful for long-term evaluation. It helps us analyze the overall performance of a portfolio or a trading strategy over time, and it can provide insight into what might work and what might not work. It especially excels where there is no technical formula, like some of those Black-Scholes models and the variations of the Black-Scholes models, which doesn't assume normally distributed volatility. Those kinds of models which don't have an analytics closed form solution or exotic options, for example, in and out options, those things which do not have an analytic solution. Monte Carlo is an ideal method to evaluate the exact pricing structure for those things. So if you want to price an exotic option, you have to use Monte Carlo. But for stock trading, making decisions based on changes in microstructure or macrostructure, that's where we have to use the TD learning method. The dynamic programming can be theoretically used if we have a perfect structure of the model, like the Markowitz model, which has a perfect structure of the model. But we all know that market is so dynamic. Dynamic programming is even though the name is there, that it matches with the dynamic nature, it's really not feasible to use dynamic programming for any kind of stock market trading strategy. Now, in the past few examples, the real use cases we talked about, the dynamic programming was a very poor choice. Now, let's talk about a case where the dynamic programming is the leading choice. For example, in warehouse management, knowing when to restock and optimize inventory is crucial. Otherwise, there is high holding costs. In fact, that's something people constantly manage. Even there are books, Profit First and stuff like that, which talks about inventory management. Because sometimes when we wait for inventory to be dispensed, our bottom line can totally fall out and we can lose money. And a profitable business which is actually making money, has lots of clients, can go bankrupt if they don't manage their inventory properly. So that's a very crucial thing for any business, is inventory management, calculating holding costs, calculating when the money is coming in, calculating when the money is going out. If the money is going out before the money comes in, guess what? you'll overdraft. And if that happens over and over again, guess what? You might go bankrupt. So those are the things that needs to be handled very carefully, and you need experienced managers to handle those things. Now, this is where the dynamic programming comes in. So if you have the small companies cannot do this, but if you're a big company, then if you manage a big company, then you can create reliable models, because you have past historical data of inventory, historical demand, seasonal historical demand. So you know exactly day by day, week by week, what the demand is going to be and what kind of inventory level you're going to maintain. And you can possibly also forecast what the pricing going to be, because usually companies buy options on consumer goods. Like, for example, if you're Gap or any retail clothing store, you'll probably buy options on cotton, because then when you're buying the raw material, or even if they buy the finished products from wherever country you're sourcing from, you have to hedge for the cotton prices, because if the cotton prices go up, then your profit margins will get eaten into if you are not hedged. On the other hand, if you have a smart chief executive, chief financial officer, CFO, who has already bought those cotton futures, then those cotton futures will rise up in value, so you're essentially balanced out. But you also need to predict how much the demand would be in order to buy the bulk of the futures. So this is a very complicated system. Let's say you need 10 million orders of garments, $10 million worth of garments, then you should buy those futures whose payout would be equivalent to those $10 million, so that if the cotton prices fluctuate, you actually don't lose money, because then your option values, your future values go up in tandem. Even though you're losing a little bit of profit in the actual sale of that product, you actually can immediately sell those futures that you have purchased ahead of time and recover that lost revenue. So you get balanced out. So those are more technical subjects. I don't want to get into that. But here we know the entire history. We know how the demand is going to progress, and everything can be codified in a whole machine learning pipeline, a data pipeline, and there all the data can be ingested, and a machine learning, reinforcement learning pipeline can be trained on this fully known environment, and then it can make decisions. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.